yesterday.
Thank God that I remind you again.
Yes, excellent. Yeah, thank you.
Yeah,
I didn't want to miss this one.
Try sharing the screen once.
Yes. Okay. I share my screen. Okay.
No, not you.
Jiri, yeah.
Yes, I can.
Yeah. We will try it once.
Well, now it's.
Thank God that I remind you again.
Yes, excellent.
It's 5 o'clock.
I
didn't want to miss this one.
Try sharing the screen once.
Yes. Okay. I share my screen.
No, not you.
Jiri, yeah.
Okay. Purvita, please. We will try to stop that.
Yeah, just a minute. There is some problem.
It's 5 o'clock.
I didn't want to miss this one.
Okay.
Okay.
We'll wait for a couple of minutes.
Yeah, sure. Actually,
By
again,
the way, Fred, has he met sometimes?
Hey, pardon me?
Fred, has he met sometimes or not?
Yes, we met a long time ago in Brno.
I think so, yes.
Yes, it was for the defense of Václav Slavík, I believe.
Oh, yes.
I think I tried to contact you by email a few times and it bounced back or something. I don't remember. Yes, I wanted. So I'm glad to see that you are still alive and kicking.
Okay, so we have 12 participants now.
Let me see the Shashank Pata.
Yeah, I think we can wait for a couple of minutes because participants.
Yeah, participants are still joining. Yeah.
Yes, I see lots of names. I don't know.
And Jam sent an email saying that he cannot attend today.
Oh, okay. I didn't notice it actually. Just now or just after?
Yeah, just now.
Okay.
Purvita, you're still playing badminton against the peacocks?
Oh, not really. Now all the doors are closed. I'm not doing anything.
Okay. Purvita, can you make me the co-host?
Oh, you are not? Oh,
yeah, I can't see anyone.
Yeah, I just forget. Yeah. Yeah, now you are the co-host.
Right. Oh, Fosco is here as well.
Oh.
So Mike is still there, Mike Lieberman?
You are asking to Jiri, I guess, right?
Ivan, how did you learn about this presentation?
Sorry?
Hello, Jiri. I saw the announcement on Zulip, a category theorist chat.
So you are a perfect spy.
Sorry?
You are a perfect spy.
Yes.
Wow. We are getting many people from outside today.
Yep.
Because
it's
someone
from category theory group, I guess.
Yeah.
Yeah, someone has advertised this meeting online.
The advertiser is also here. Yeah, Shantan is here. He advertised this. Yeah, I think we can start now.
Yeah. It's time. It's already set.
Yeah, so very warm welcome to the final seminar of this semester. We'll meet again after winter break. So I'm very pleased to have my postdoc supervisor, Professor Jiri Rosicky from Masaryk University, Brno. He's an expert in category theory, like I don't think I need to introduce him. Mostly famous as the author of this book on locally presentable and accessible categories. And yeah, one of the major contributors in the theory of accessible categories, algebra model theory, and its applications to algebra model theory and homotopy theory. So he'll be giving a talk on from first order logic to accessible categories. Over to you, sir.
Yes, so Amit, thank you. Thank you for inviting me for this talk and for introducing me. That's a real pleasure to see you again after years you spent here, or year you spent here in Brno. Yes, I was advised that this talk will be for graduate students, so I shouldn't assume too much. So I hope that I will not disappoint those who are much more advanced. I will try somewhat to adapt it, but of course, interrupt me if something should be explained, if I have to say more about subject. So as the title suggests, it should be some kind of propaganda or introduction, how categories can be used to do abstract model theory. So under first order logic, I mean here, just say predicate logic to begin. The goal of model theory is to study structures by means of logic. So your structure is just a set equipped with some operations and relation. In the simplest case, these are universal algebras. And in a more complicated case, you have more complex axioms like for Zermel or Frankel set theory. And you do it by using logic theory to do model theory. On the other hand, the category theory has a different ideology because you don't insist so much on having underlying sets and structure on them, but you more work with categories. So I would like to show you how this approach can be used and what benefits you can get out of it. So as I told you, first order theory is just a theory in predicate logic, and mod is the category of models and homomorphisms. Then what are basic properties of this category? So certain is a regular cardinal such that every model is a lambda directed union of its elementary submodels of cardinality smaller than lambda. So maybe if explanation is needed, so elementary submodel means that it is a submodel where all formulas are preserved by this embedding. So everything what's true in the model is true in this elementary submodel. And that's the known fact that any model can be obtained in this way for some regular cardinal lambda, which depends on size of on the language. So in more special situations, so I need here some classification of formulas. So positive primitive formula is existential quantification of conjunction of atomic formulas. Positive existential is disjunctions of those. And basic, it's universal quantification of these. So these are very nice formulas. You will see in a moment why they are very nice. So these formulas are called basic, and theory whose axioms are basic is called basic theory. For instance, of course, any equational theory is basic because this is just by equations. So this is just by universally quantified equations of atomic formulas. Any Horn theory, any quasi-variety universal Horn theory is given by basic formulas and so on, but it's much more general. So what's the advantage of, so that's what I told you now, yes. So what's the advantage of basic theories? The advantage is that any basic theory is closed under directed colimits of its models. So what does it mean? just here I told you that you can express any model as lambda-directed union of elementary sum models. But you don't know for general theory that if you have any directed diagram, should I explain what does it mean directed or lambda-directed?
Yeah, I think that would help.
Should I do it or not?
Yeah, it would help
Yes,
the
yes.
audience.
So
Yeah.
it means that this diagram is indexed by a poset, and this poset is lambda-directed. It means that less than lambda elements have an upper bound. So just directed means Rf0 directed, it means that any finite subset has an upper bound. So for instance, this is a known fact that if you have, so you can imagine that if you have, say, a chain of algebras and you take its union, so this is also algebra of a given theory. So union of chain of groups is a group. So this is an example of directed colimit of models. But it's not always true that you have this property, but you have it for any basic theory. So that's some of the purpose of these theories, that they are closed under directed colimit of models. In model theory, one calls this preservation theorems. That's a lot of things about which formulas I preserve by which operations, which are preserved by products, subdirect products, and also basically, in fact, these basic formulas are those which are preserved by direct colimit, one can say. So I have on one side, I have general theories. If you will remember this property, on the other side, I have those nice theories with this property. So why I mention this? So I have to give a definition of an accessible category. Say, this definition had some predecessors, but that was introduced by Mackay and Paré in 1989. So what does it mean for a category to be lambda accessible? Lambda is a regular cardinal. So it means two things. So the first is that it has lambda-directed colimits. This is why I was interested here about having directed colimits. Of course, if lambda grows, you have less those colimits, because if something is lambda-directed, it's also, say, mu directed for mu smaller than lambda, because if any subset of kind of smaller than lambda is upper bound, so any smaller subset. Yes, so this lambda colimit is weaker than having all directed colimits. That's one thing. The other thing, that there's a set of lambda presentable objects. I will tell you in a moment what does it mean. So that every object is lambda colimit of those objects from A. So this is why here I was interested in this property, because you see those submodels of kind smaller than lambda, they will be lambda presentable. I will show it, but then any model is lambda union of those. So in fact, this definition is a combination of two properties: some completeness property, existence of some colimits, and some smallness property, that any object can be obtained from small objects in this way. So this is, in fact, very, very weak. For instance, predecessors of those lambda accessible were locally lambda presentable, where you assume all colimits. Here, really, you minimize the assumption on the existence of colimits, but you have enough of them to do this. So in some sense, one can say that this is category which behaves well with respect to lambda colimits. Of course, this definition needs to tell you what's lambda presentable. And obviously, lambda presentable, if its home functor preserves lambda colimits. So now the definition is complete, yes, because I explained what is here. Why the name lambda presentable? I think everybody knows what's finitely presented group. It's a group given by finite many generators and finite many equations. So in algebra, one has well-established concept of finitely presentable or finitely presented. And this is a categorical formulation of that, going that's much older than this, going to Gabriel Ulmer in 1972. And this categorical characterization, it characterizes this algebraic one, in fact. Maybe just, I will give you examples in a moment, but now let's finalize terminology. So category is accessible if it's lambda accessible for some regular cardinal lambda. So that will be the basic concept of this talk. So, and just to go back what I told you, if you have basic theory, so this category is accessible because it has all dialectical limits that was shown or mentioned, and those small objects are those having kind smaller than lambda, and these are lambda presentable. Just give me a second to explain that. Yes, so if you have good theory, so then the category of models is accessible. So examples, for instance, sets, the category of sets. So any finite set is finitely presentable. Why? So imagine that you have a, maybe I could just make a picture. Yes, you have here a directed union of sets, and you take element in the union, so you have a mapping from 1 to here. So certainly this element should belong to some member of this union, which is exactly this definition that this home factor of this thing present those coordinates. If you somewhat think what it means, or exactly means what I showed you with finite sets. So the category of sets, pose sets or groups are finitely accessible, and these finitely presentable objects are finite sets, finite pose sets, or finitely presentable groups. Again, if you take a union of groups, so you have finite many generators, they should belong to some member of the union, and the finite equations that should be satisfied in some member of the union. So this is why finitely presentable group is finitely presentable in this sense, and vice versa. Yes, so this is in fact a category theory way how to define presentation without having sets and elements, just having a category. So this is this basic concept of contrastable category, which I want to compare with, say, the classical model theoretical approaches and mention some advantages or disadvantages. Sorry. So maybe another example which might be interesting for someone. So take complete metric spaces and contractions, or Banach spaces and linear contractions, or Hilbert spaces and linear contractions. I have to say that with these metric spaces also, I allow distance infinity. Otherwise it wouldn't work. So distance also could be infinity. With Banach spaces and Hilbert spaces, that's just usual thing. So these categories are L1 accessible. And those L1 presentable objects are always separable things. So those having countable dense subset, which is somewhat quite easy because this cardinality is countable, and without this closure in some sense they disappear from here. So this is another example. And for instance, in continuous model theory, one which is model theory, say, over metric spaces. So then instead of cardinalities of underlying sets, one takes these density characters. So cardinality is small is dense subset. So why? Because these are instances of the same concept or only presentability from category theory. So again, I will mention it later. So these are some examples to these situations. So there are really plenty of examples of flexible categories. And if you have now any first order theory, it doesn't need to be nice. So then the category of models now and elementary beddings. So not homomorphisms, elementary beddings, this is always accessible. Yeah, so one can somewhat summarize that if you have first order theory, if it's nice, if it's basic, so the category of models and homomorphisms is accessible. If this theory is more complicated, so then the category of models and elementary beddings is accessible. So, but not only this, up to now I have spoken only about first order theories, but you can in fact take infinitary theories So I take the language L kappa kappa, which means that I allow conjunctions as injunctions or less than kappa formulas, and I allow quantification over less than kappa variables. So this is language L kappa kappa. So I have any theory of L kappa kappa. I take the category of T models and now kappa elementary embeddings. It means elementary with respect to those formulas which are here. So this is again accessible. So one S is missing here. Sorry for this misprint. And if the theory is basic, then the category of T models and homomorphism is accessible. So this is not a specialty of usual first order theories which are finitely, but it is true for, in fact, also infinitary theories. I have to point out that also you can have also infinitary function and relation symbols. Yes, this is that you have to quantify over infinitely many things. For instance, if you want to axiomatize well-ordered sets, so you need then omega 1 for kappa to get it. So one can say that accessible categories correspond to categories models of infinitary logic. And that was the purpose of this book of Macca and Paré. The title somewhat says that accessible categories is categorical model theory. But not much was done after publishing this book. It took some time to really to use this recommendation. So this is my starting point. I hope that at least if not everything was clear technically, so I think the intuition could be followed now. Yes. So accessible categories, they correspond to categories models on infinitary logic. That was another attempt to do abstract model theory devoid of, say, formulas, and that these are abstract elementary classes of Scheller from 1987. So still, he keeps something here. So one has a signature. It means one has a list of operation and relation symbols, which are finitely here. So this is just first order signature. But now one take the category of sigma structures and embeddings. So one takes as embeddings as morphisms. Of course, one could, this is between homomorphisms and elementary embeddings. But now one doesn't use formulas to specify a subcategory as a category of models, but one takes any subcategory. I have to say that Scheller didn't use this category language, but I use it, but this is the same thing. So one has a class of models. And also, one chooses not only models, but also chooses those good embeddings. One doesn't need to, you take usual embeddings, you can take elementary embeddings, but also you can take something in between. So it means that you don't use formulas, neither to define models, nor to define homomorphisms. So you have, one can say, an abstract and subcategory of the category of models and embeddings. The subcategory is not full. It means that you don't need to take all embeddings. You take only some of them. So you choose some models and some embeddings. So when this creates an abstract elementary class, so first condition, K is closed undirected coordinates. This is what I mentioned before for basic theories, for instance. The second condition is called coherence. It means that if a composition of two morphisms, such that the composition and the second one is chosen, is a chosen embedding, so the first one is chosen. For instance, if you take all embeddings, so that's easy to see that if a composition is embedding and the second is embedding, then the first is embedding. Or if you have elementary embeddings, if the composition is elementary, the second is elementary, the first is elementary. So this is very natural condition is coherent, so it's assumed in definition. And the third thing is Leidenheim-Skolem transfer condition, which means that some cardinal, so if you have a submodel and B belongs to the class, so then you can enlarge this A to A prime, which A prime belongs to K, and also this morphism belongs to K, and you don't increase the cardinality too much. For instance, in usual model theory, if you have a a subset or submodel, so you can extend it to elementary submodel, but not adding too many elements. So this is the condition which is the sad one. So that's the model theorist approach to do abstract model theory, not to use categories at all, to still keep signature, to still keep sigma structure. It means to still keep underlying sets, but not to use formulas. Instead of formulas, you abstractly choose objects and morphisms. So what's the relation with these? So the first thing is that every abstract class is an accessible category with identical limits with morphisms and monomorphisms. It can be quite visible from the definition because this is the smallest condition. Just one has to show that these objects which have small cardinality are lambda presentable. You have identical limits, morphisms and monomorphisms. So this is an easy observation that this definition belongs to this accessible web because this is such accessible category. Now, if you have basic theory of L kappa omega, it means arbitrary conjunction and disjunction, so kappa array, but only finite quantification. So any basic theory of this gives them, again, this T is double, is an abstract elementary class. This is an example. In some sense, this abstract elementary class is generalized categories of models with finite quantifications. So now I should mention two conditions. What does it mean to be isofull? So when you have a subcategory, it means that you have less object, less morphisms. And isofull means that you take all isos. So if you take an isomorphism in this category between chosen objects, so it's an isomorphism, it belongs to K. And coherent is the condition I had before. So if the composition and the second one belongs to your subcategory, so the first one belongs to it. And then the final result is independently obtained by me, Tibor Becker, and Mike Lieberman, that the category is equivalent to an abstract elementary class if and only if it is an actual category. With identical limits, whose morphisms are monomorphisms, and which admits an isofull and coherent embedding into a finite flexible category desiring identical monomorphism. So you see, this is not a difficult thing, but it took, in some sense, quite many years to realize this connection between abstract elementary classes and actual categories. But this is, again, I repeat that not because that's something difficult to realize that, but simply because those two communities were quite disjoint. So then, at the same time, we realized that you can somewhat characterize abstract elementary classes among accessible categories in this way. By natural conditions, I mean identical limits and monomorphisms, and somewhat maybe less natural conditions of these, and instead of to sigma structures to really to don't do sigma structure at all, so I replace it by finite accessible categories. And this embedding should be good, so it should preserve these and these. Sorry?
Can I ask something?
Of course.
So why do you call it coherence condition? Like,
yes, so now you see this coherence condition looks quite reasonable, and probably you cannot do this theory without this condition.
Okay.
This isofullness that looks, I don't know any instance where I need it, in fact, but on the other hand, I don't any reasonable example where it's not satisfied. Because if you choose morphism in some reasonable way, you always include isomorphisms. So it's very hard to choose morphisms and not to take all isos.
Right.
So these conditions are quite natural in some sense.
Okay.
This coherence is this fact I told you that elementary embeddings are coherent and embeddings are coherent, and that for some think it's needed.
No, I mean, why the name? That was my.
Why the name?
Yeah.
Yes. So yes, the name is not nice because it's overused. So in fact, with Tibor Becker, we wanted to avoid it, and we used nearly full.
Okay.
But then we came back to coherence, which is used by model theory. So you see, sometimes that's difficult to find name which is
Right.
original and good. Now, immediately it appears one question. And for model theories, that was quite easy to give example that you have structures. You take an abstract memory class within these structures. And that within these structures, you can axiomatize it by such theory. You see, otherwise, one can ask you why to introduce those AECs, abstract memory classes, because you have these nice theories which finite quantification. So that's easy to give such an example. But this is not what category theories would like to know. Category theory would like to know to find an abstract elementary class which as a category is not equivalent to something which can be axiomatized by such theory. Yes, because you see, you are allowed to change underlying sets, allow structures. Only thing which you are interested in is which category you get. And then, of course, all categorical properties, I will tell you that important properties in model theory are categorical. All categorical properties are shared with this equivalence. So for me to really show that these AECs are more general than these things, then one would give such an example, which is hard. We tried to find it with Mackay, we failed. We had a candidate for it, but we couldn't prove it. And that was Simon Henry, who was postdoc in Brno at that time. He showed that our example we wanted to do. So you take category uncountable sets and monos. So simply your signature here is empty. Of course, you cannot characterize uncountability using finite quantification. You can characterize countability, but not uncountable. So evidently, these uncountable sets and monomorphisms are not abstract elementary class within sets. But you have to show that it's not an abstract elementary class at all, which means that you should understand in some sense how, I will come to this once, you have to understand how functors into sets from this category which preserves that we call it its look-like. So this was for me quite a breakthrough, and I will come to this point later. But now let's introduce something which is important. So I am coming back to beginnings. So and presentable objects is object is lambda presentable for some lambda. So any object of x category is presentable. That's easy. Then having an object with the smallest lambda, say it is lambda presentable, it's called the presentable rank of A. Yes, so you have an object and you take the smallest cardinal, say the lambda presentable. And if this presentable rank is successor, so then U is called the size of A. So this is very important because you just using a category, you can define size of objects without having underlying sets, because usually size of an object is correlated with underlying set. But for instance, in this continuous model theory, the size of object is density character. So this is exactly some instances of this definition. So this is a key how to get sizes to abstract categorical setting. So then size of infinite sets is cardinality, the same for pole sets and uncountable groups. The size of infinite complementary space is density character, the same for Banach spaces, infinite dimensional, and the size of infinite dimensional Hilbert spaces is its current orthogonal base. I don't hit something here. So you see, if you have Hilbert space, so its size is cardinality of its orthogonal base. So in some sense, its size, it's maybe more dimension than cardinality, but it really gives you nice, that was my mistake, that gives you nice way how to define sizes in the abstract setting. So just to give you an example. So take infinite dimensional Banach space, and it's known that it has cardinality lambda to LS 0. That's a real result in Banach spaces, which means that you cannot have Hilbert space whose cardinality has countable cofinality. But there are Hilbert spaces of any size because you can take any cardinality as a base, orthogonal base. So in this category of Hilbert spaces, sizes never start to coincide with cardinalities. There are arbitrarily large gaps of cardinalities, but not in sizes. So this concept of size makes really infinitary model theory, where also arities could be infinite, more manageable, because in Hilbert spaces you immediately get arbitrarily large gaps of cardinalities, but not in sizes. So the sizes smoothen the situation much. And that we showed with Tibor Becker that if here accessible categories are colimits, so then these presentable ranks are always successors starting from some cardinal. So it means that you can speak about sizes. Without this assumption about a colimit, so it's true under GCH. In AC, in surrounding class, sizes always epistropated, so it eventually coincides with cardinalities. And so there are not arbitrary large gaps of sizes. So it means from some moment you have objects of all sizes. This is upwards Lagrange-Coulomb theorem. And we didn't follow it as a problem because we saw that it could be an easy counterexample, but it's not so. So it's not known whether there are accessible categories, even if they colimate with arbitrary large gaps of sizes. Yes, so in some sense, the question is something like upwards Lagrange-Coulomb theorem is true here. Yes, you have just accessible categories, even if they colimate is quite nice, but such that you could have objects of sizes and objects and sizes without objects which changes up to the end. So there are the large gaps of sizes. It means sizes without any object. We called category as accessible. This cannot happen. So there are some results about these categories. So our result was that any accessible category is a colimate, which tiny colimits are nice. It means they are preserved by forgetful functor to sets, faithful functor to set. So then it has this property. Another result, which is in some sense better with Mike Lieberman, is that whenever morphism monomorphism, so then it's always less accessible. So here in this world, accessible category is a colimits and morphism monomorphism. So there are not arbitrary large gaps of sizes. This is quite a pleasing result. And a kind of benefit of this is that if you take Hilbert spaces, and this R means that you take not contractions but isometries, linear isometries. So this usual forgetful functor from those Hilbert spaces to sets preserves all one-dimensional coordinates. The same is true if you take the category of commutative C-star algebras. And what we showed with Mike Lieberman and Sebastian Wasser last year, that there is no faithful functor for those Hilbert spaces and isometries to sets which preserve direct coordinates. So you see, when I mentioned this solution of Simon Henry, so I told you that we have to look at functors, faithful functor from uncountable sets to sets which preserve direct coordinates. So of course we have the same problem for this category of Hilbert spaces. And here there is none. There is no faithful functor which preserves directly coordinates, not one directed. And somewhat benefit of this is that the category of commutative algebras can be axiomatized by any first order theory, which is an ultimate solution of the problem stated by Paul Bankston in 1982. In 1984, independently, Bernard Banaszewski and me, we showed that it's not possible for order theories whose models are closed under products. But this result shows that it's not possible at all. So this is a kind of application of this category theory techniques. But let me to go back to this problem that you have now accessible categories, they call it monomorphisms. Yes, so you have this, say, nice category, and now you would like to know whether it's an abstract elementary class. So the first question is that you can embed it to some sigma structures. But you're just a category. You don't know which operation relations you can take. And the way how to do it is, so whenever you do it, so then of course you take this embedding and this forgetful functor, so you immediately get out of it a faithful functor which preserves the coordinates. But that's a way how to get a possible stack of those operation relations. Although one can replace operation by relation, so you can assume that the stigma contains all relational symbols. And now this idea, it goes back to Lovier, in fact, to his dissertation that you can replace operations by natural transformations between forgetful functors. So here you define another relation symbol as a subfunctor of this forgetful functor. So you see, so I have to tell what I am doing. So of course, if I have just these actual categories and coordinates and monomorphisms, I don't have this forgetful functor. So there's no way how to guess which operations and relations could be there. But if I have forgetful functor, it means that if I have underlying sets, so I get a possible candidates for relations. And these are those which are somewhat implicit because they are subfactor of these. And this gives you some understanding of those faithful functor from K to Z which present the coordinates. Yes, so this is, you see, this is an approach how to, again, maybe here I should stop for a moment. So I have something very abstract, faithful categories and coordinates monomorphisms. And I would like to see whether it's an abstract element class or not. So it means that I need some good forgetful functor to sets and enough of operations and relations such that it events. So if I don't have this functor, so I should look at those functors and check it. If I have this functor, so then basically I'm in a good situation because I can get these relations. So this program reduces the study of such functors, faithful functor to set which present coordinates. And now this is, in fact, what Ivan de Liberty and Simon Henry did, and which was used by Simon Henry later to give this his counterexample, that you just take actual categories and coordinates and look at all functors to set with present coordinates. And these functors form a category, and in fact, this category is a Grothendieck topos. So on these functors, you have a very rich structure. You have a structure of a topos. They call it Scott topos because it generalizes the usual Scott topology on direct and complete posets. So, and on the other hand, if you have Grothendieck topos, so you can take its points, which means functors from this topos to sets which preserve colimits and finite limits, which correspond to geometric morphisms. So then the category of points is infinite omega elementary. And in fact, these infinite omega elementary categories, it means, I mentioned it before, these are categories can be axiomatized by infinitary disjunctions and finite quantification. They are precisely categories of points of Grothendieck topos. This is well known. But in this way, they in fact obtain an injunction between accessible categories, very colimits, and functors which preserve very colimits, and category of Grothendieck toposes and functors preserving colimits, finite limits between geometric morphisms, where S is the Scott topos. Simply you take this category and take all these functors, and having this topos, you take its points. You go ahead and back. So you see here, you don't try to find a good functor which makes this K abstract class. You simply look at all possible functors, but you have a rich structure on them, a structure on topos on them. And using this structure, you can, in fact, using this structure, Simon Henry showed that these uncorrelable sets cannot be axiomatized in this way. So this S of K, this Scott topos, it in fact bears knowledge about all possible relations which can be interpreted in K. So one can say it plays the role of full infinite omega theory of K. Yes, so here I spend some time how to pass from abstract thing to concrete thing. the unit of this adjunction, in some sense, that interpretation is that it may scale to the category of models of its full infinite omega theory. So I will take all possible, so I have a category. I take all possible forgetful functors and all possible relations for them, and this is this embedding which I get here. So it should test whether this K is an abstract elementary class or not. And when this functor is faithful, no, if and only if there's a faithful functor from K to sets which present like coordinates. That's evident. And now if this category is now good, if it's elementary, then you get also by adjunction, you get reduct, you get reduct back. So it means this splits and you get such functor. And in this way, if you have such splitting, this makes this elementary. And in this way, that was proved because he showed that these points of the Scott topos of uncountable sets and monos, this is the same thing as point of Scott topos of countable sets, which is just the category of countable sets and monos. And this is so-called Schwanuer topos of it. And this is now clear. This category is, of course, abstract elementary class, but this cannot be because they have the same classifying, the same Scott topos. So this was how we did it, by understanding this passage. So maybe that was some quite, maybe not much elementary category theory. So that was a way how to somewhat pass from abstract to concrete in the most abstract way, that I take all possible passages, they organize to a topos, and you can use topos theory to study these properties. Good. Now I should mention that this seems to be a strong tool for studying SQL categories like coordinates. But now I would like to pass now to something which somewhat justifies this approach. Yes. So again, I come back. So I take SQL category coordinates and lambda is anti-cardinal. So what does it mean that K is lambda categorical? So this is a concept of model theory. A theory is lambda categorical if it has exactly one model up to isomorphism in lambda. So this is a classical subject of model theory, to study categoricity, to study at which cardinals you have exactly one model up to iso. But since we have the concept of size available, so we can define for our abstract category. I take that coordinate because here we know that any object has a size because its presentable ranks are successors. So I define that is lambda categorical if it has this property. But now what's important to see here, so imagine that you have a category K, which is, for instance, an abstract elementary class in one signature, and you take another signature. So maybe underlying sets could differ in that signature, but this concept of size doesn't differ because it's a category concept. It just depends on the category. So this concept of categoricity, in fact, doesn't depend on underlying sets. It's a concept of category. So this is why this question, whether that's an abstract elementary class, which is not axiomatizable by kappa omega in this categorical sense, is important, because if it would be true, then you don't need to study categoricity for ACs, because it's enough to study categoricity for these theories of finitely quantification. So this crucial model theoretical property is in fact just a property of a category. It doesn't depend on concrete presentation by sets and formulas. And now this is this famous shas categoristic conjecture, which claims that for any elementary class, that's a kernel kappa, such that starting from kappa, it's categorical in all cardinalities or in none. This was motivated, you see, the history is that was conjectured by Losch, Polish mathematician, for spheral theories and a counter signature in 1954. And it was proved by Morley in 1965. And the proof of Morley, that was really breakthrough in modern model theory. He introduced concept of stability types and these things. So, and he proved this Losch conjecture. And Shelah extended it to uncountable languages from countable languages. And then conjectured it for assignment classes. And in some sense, for tens of years, it was the main test question for AECs, which somewhat was the dynamo which put this theory ahead, that people tried to decide this conjecture, that it's true or not. Of course, he formulated it using external sizes, using cardinalities, but they coincide with internal sizes, starting from some cardinal and always eventual here. So when it starts from some cardinal, that's the problem. So this SCC, this Shelah categoristic conjecture, is a property of an abstract category, not a property of a category presented by sets and operations and relations. So one can even ask whether such conjecture could be generalized beyond abstract classes to actual categories directed coordinates. We, with Tibor Becker, he haven't dared to do this because we expected an easy counterexample, but it didn't happen. And you see, for instance, maybe just let me do it again. You see, if you find an accessible category with arbitrarily large gaps of sizes, so just I show it here that all the time you have model, you don't have model, you have model, you don't have model. Then you can just add sets to it, which means that here you will have two models, here you have one model, here you will have two models, you have the one model. So if you find an accessible category, then it coordinates with arbitrarily large gaps of sizes. So by this trick, you can find an actual category that it coordinates, which doesn't satisfy this categoristic conjecture, because you have arbitrarily large cardinals where you have two models, and arbitrarily large cardinals when you have just one model. So one could get getting counterexample to these gaps of sizes, but that's not known, surprisingly, because what we expected that one will get some easy counterexample showing that Shelah was right to formulate his conjecture for ACs. So it doesn't seem to be true. And maybe something like to end of this story, but nearly end this story. So let's say, prove this conjecture for universal ACs. Universal means that they are closed under submodels. You see, usually universal theories are given by universal quantification. They are closed under submodels. Here you have to say it in this semantic way. And in joint pair with Shelah, having a general elementary class, so they assume the existence of proper class of strongly coupled cardinals, so assume some set theory. So then again, they prove this conjecture. And very recently, Christian Espindola, who is currently postdoc in Brno, who used, maybe that was not totally accurate to call it Scott junction, to make, I will tell you what would be more accurate, to transfer this problem to topo theory. And in fact, he proved, and he used classifying toposes for that. I will mention what does it mean. So he proved that if you have an accessible category with directed coordinates whose morphisms are monomorphisms, so this nice thing, accessible directed monos. So then assuming the proper class of strongly coupled cardinals and GCH, then this conjecture is true. He used classifying toposes for this. Classifying toposes is something quite related and much more classical than Scott toposes, that you usually, for instance, if you have a group, so you can define this group categorically by Lowie's theory, that you, instead of operations, you take morphisms from, you include operation to Lowie's theory, to finite product theory. And more generally, you can sketch more general theories using RS1 sketches. But in some sense, you complete this sketch or this theory to a topos. And this completed topos is a classifying topos. It has the property that geometric morphisms to a category corresponds to models of this structure. So we use this classifying toposes to do this. Yes, I hope that this is correct, what he did, because that would be something really fantastic, because it would, you see, there were thousands of pages written about Schellach categoristic conjecture. So it would be possible to transfer it to topos theory and prove even something more general than this, so that would be something which is hard to believe. Yes, so now I am at the end of my slides, but also just I would like to say that I omitted many things which I don't want to omit, because one of these advantages of categorical approach, I mean to forget about syntax, is that you can, something which is very important, I mean, that is called in model theory forking or stable dependence, which is, at least for me, quite hard to read. So you can replace it by category theoretical approach just by giving a good calculus of commutative squares, which, if your category has push-outs, are push-out squares, but you don't have push-outs in model theory. So that's a good calculus of squares, which is equivalent to the stable independence. And a benefit of that we did together with Mike Lieberman and Sebastian Vassey, a benefit of it was that the stable independence, which appears here, so in a special situation, the special situation is that you take a, let me again to jump in the that you have a category and you choose some good class of morphisms, for instance, embeddings. And now you do something like model theory with that. And then you can speak about stable independence here, which would be calculus of squares consisting of M morphisms. And it turned out that under some assumptions, which are quite reasonable, the existence of such stable independence for this class of N is equivalent with the fact that this class is cofinitely generated. This is a concept from homotopy theory. Cofinite generation, does it mean that this class is generated from a set in a good way? So replacing formulas by categories, replacing forking of stable independence by category concept of good calculus commuting squares, in some sense unexpectedly can connect model theory with homotopy theory, because these good classes are those which are good in the sense of homotopy theory. It means that they are cofinitely generated. So that's all what I wanted to tell you. So I promised to be elementary, but now I don't have this feeling at the end. But of course, time is limiting, so I couldn't stop. Maybe longer at some issues which I should. So, but you can ask me. So thank you.
Yeah, many thanks for your talk. I mean, it's I think it's been ages even for me that have looked at this material, but I'm really happy with the progress and lots of advancements in this field. Any questions from the audience?
So maybe you have a question?
Yeah.
Yes.
Okay, so you defined abstract elementary classes, and so Sherlock's categoricity conjecture is stated for just ordinary first order logic, or more generally L kappa kappa. Is it also stated for infinitary logic, or are the things a bit different there?
No, under infinitary logic, I meant logic with finite quantification.
It's 6 o'clock.
Yeah, finite quantification.
Because then, in some sense, Sherlock wrote a paper claiming that maybe there's no good model theory with uncountable quantifications. Yes, so really that was infinitary logic, but with finite quantification and also finitary symbols, which in some sense, absolute elementary class gives an abstract generalization of that.
Yeah.
That's important. Yes, that's important. But and still, it's visible here. It's visible here because everything depends on the existence of directed coordinates, which in some sense is this, how to say, this trace of finitary here.
Yeah.
So even I don't know anything about accessible categories with direct coordinates. I can repeat, I expected a simple counterexample, which is missing, but that should be a counterexample, I believe, but it's not. Yes. So thank you. Maybe I was not clear enough here.
Okay, I understand. Okay, so yeah, for example, you can if you replace just directed colimits by lambda directed colimits, then it could get, you could define this.
Then things terribly complicates, yes.
Yeah. I see.
And there should be counterexamples. Sure, but we don't have any, surprisingly, because even, for instance, these Hilbert spaces. In Hilbert spaces, that's a typical counterexample that model theory doesn't work because you have an arbitrarily large gap of side of Carnot's underlying sets.
Yeah.
In Hilbert spaces, you need omega-1 quantification to get it. You need logical omega-1 for this, yes?
Yes.
Then, of course, there are Hilbert spaces, not in all cardinalities, but, but in all sizes. So this concept of size gives you a chance to go beyond that, but things, yes, that's open. Certainly, that would be nice to progress, but let's hope.
Any other questions?
So maybe I also wanted to ask, I'm sorry. Yeah. So you defined the concept of size of an object in an accessible category. Does everything trivialize if you consider categories obtained from posets? Like a category, like between two objects, you have at most one arrow.
Yes, they did think category, yes, but then these categories, yes, to be accessible, then you need something like Scott domain or something.
Yes, absolutely.
Compact objects.
And the concept of size, what the...
Yes, in fact, but also you need that this category small.
Yeah, so let's not say they're small.
No, this category is never large because if you have a large poset, so you cannot have it.
Right.
And basically everything here is done for large categories because you have small categories since eventually, so you can jump over this. And so for posets, somebody it loses interest here.
Yeah.
From this eventual point of view.
Yes, you are right, because there is only a set of finitely presentable. Yeah, that's right.
Yes. You don't have a chance to get large.
Yeah, you won't have a chance to get a large posets. Yeah, so my question was stupid. Okay.
I think this is good illustration, in fact. Yes.
Yes. Oh, and there is in your definition of an abstract elementary class. In point 3, you say that A prime is less than A plus lambda.
Yes, let me to go back to this. I was maybe too brief with that. Yes. This is real, just simulation of Lemma's column, yes? You have a...
Yeah, here at the bottom, it's A plus lambda.
Sorry, that?
So at the bottom, it is cardinality of A prime is below cardinality of A plus lambda.
Which means that, well...
So take A prime equals A.
It means that below lambda, it doesn't, is lambda, and above lambda, it's the same as A.
And
if lambda is smaller than A, so that's just you can avoid it, so it's the same.
Yeah.
And so, if to deal with things like finite, to go to infinity, that's only.
So, okay, I'm a bit confused. If you take A prime equals A, then it works on.
No, but for that you need that A belongs to K, which we don't know.
Oh, yes, okay. I missed this. I got it. Okay.
It's not a model, so you can extend it to a model.
Yes.
But not
okay.
Too much. Yes, probably I was too deep with that. Yeah. Yes.
Okay, now I get it. A prime belongs to K. A prime belongs to K. Yeah, thank you. I get it now. Oh, thank you. So, yes, okay. If you, I have a question about L infinity omega. So I think it more or less enters at least the first third of your talk. So you consider a proper class of axioms?
No. Always theories.
Oh yeah, you always have L kappa omega. Okay, yes.
And here, whenever I have L kappa omega, so symbols are finitary.
Yes.
Whenever one does it, so symbols are finitary, and a theory is just a set of axioms.
Yes. I see. Yes. Okay. Thank you. Accessible.
Yeah. Can I ask a question? Yeah.
Yes.
So the work that we did, we were thinking about the first order version of that, full first order version. So do you have an answer now? It seems so. The replacement for the collection of the class of objects amongst the ultra categories which Mackay had introduced. So the ones which correspond to pre-toposes, like a complete two-sided duality between pre-toposes and something else. So do you have an answer of that now because of this ACCW? And
I don't see that. Does it relate to these ultra categories?
I mean, ultra categories had some extra set theoretic assumptions. Perhaps you can replace them with these extra functors which you have, which preserve directed colimits down to sets.
No, this is not clear to me. You see, I think when we spoke about that, that was probably before, because Lurie used ultra categories. Do you know it? Yes.
Sorry?
Jacob Lurie used ultra categories.
Okay. Okay.
You know it, do you?
No, I don't.
So I should look at it because he is some kind of genius. Yes. So he uses ultra categories on his webpage. That's something about that. But we never linked these things to this ultra approach. Yes.
Okay.
I don't know.
Can I answer to this question?
Yeah, sure.
It's Ivan here.
Yeah. Hi.
So in fact, this is partially in my PhD thesis because every ultra category induces a ENAD, which was introduced by Richard Gardner, and in the thesis I provide an Isbell duality for ENADs and topoi, and so this should lead to a sharp characterization of what Mackay did, and those should be compact Hausdorff E-nuts, but this is not in the thesis. This is just conjectural. So to answer the question, it's not precisely connected to the Scott adjunction. And the answer is in a sentence because Scott is not always sober. That's the answer in a sentence, but if you don't know the literature, maybe it's not a good answer. But the point is that the Scott adjunction cannot capture completely the topology that is on your category, and so you have to do something more clever there.
Okay. Thanks, I will have a look at it.
Thank you, Ivan. I have forgotten to this.
I had a query actually.
Yeah,
so actually, here I can see that like for every basic theory T of L kappa omega, T is an abstract elementary class. So is there any possibility to think about geometric logic and accommodate the notion of, because in geometric logic I do have arbitrary disjunction and just existential quantifier. So is there any possibility to talk about like theorem 3 about geometric logic?
You mean geometric logic with infinitary quantification?
No, a quantification is just the existential quantification.
But infinitary or just finitary?
Say finitary.
So this is also called coherent logic, yes? So that should correspond to basic formulas then, I think.
Yes, this is precisely the logic axiomatized by topoi.
Yes,
Every
yes,
geometry has a classified topos, and so the category of point is accessible and it has directed colimits. So it's in fact, it's the natural example of accessible category with directed colimits.
Okay.
This is the L infinity omega, as Jiri was mentioning.
Actually, I was confused because in geometric logic, naturally we consider the arbitrary disjunction, but the finitary conjunction. So, yeah, and
yes.
means that both of them are infinitary or something like that. So, kind of confused.
Yes, so that you take basic theories, yes, in this terminology, yes. Which is more special than general infinitary kappa E omega, yes.
Yeah. Any other questions, or shall we declare that's okay? So let us announce. Yeah, thanks a lot once again. Yeah, we are really happy that you could come here.
For giving such a nice talk.
I'm not really sure like how many participants had the background knowledge to get the gist of it, but those who understood, yeah.
Category theory group, so
yes,
I guess many of them had.
Yeah. And no, but like those who understood it, yeah, it was really an excellent
It's really nice. It's really
nice. So we will meet again in January.
Yeah,
we'll have a break for the entire December and we'll meet again after the break.
And I guess that we would like to again say that if someone is interested to give a talk in this webinar, please write to us. That will be wonderful, I guess. So.
Yeah. Yes, Fred, I think you have more questions you can ask if the speaker has time.
Thank you.
Yes, or you can send me email. Of course, I'm available.
Good. Thank you.